So let me just. So it's my great pleasure to welcome Paula Coelho to our seminar series for IU Commission J1. Paula is an expert on the modeling of stellar atmospheres, so especially with applications to the spectral energy distributions of galaxies. She got her PhD in 2004 at the University of Sao Paulo in Brazil, with the supervision of Beatriz Barbui, already on the modeling of synthetic modeling of stellar atmospheres. And then she continued with postdoctoral work at various institutes, among others, the Max Planck Institute in Astronomy with Guinevere Kaufmann, the IAG back in Sao Paulo, and the IAP, where she joined the group of Stéphane Charlot with a Marie Curie fellowship. Then she had, after that, went through a number of academic appointments back in Brazil at UNICSUL and the University of Sao Paulo, where she now holds an associate professorship over there. As I said, she's an expert on the modeling of stellar atmospheres with application to composite populations. And among others, I would basically say it's especially interesting, the work on alpha enhancement on old populations, especially for massive galaxies, and also the CNONA anticorrelation found in globular clusters. So today she will tell us this very Shakespearean doubt of to use or not to use model stellar spectra to study integrated stellar populations. Thank you, Paula. Please go ahead.
Thank you a lot, Ignacio. Thank you all for being here. Let me share my screen. Do you see it well?
Yep, good.
Okay, thanks. So it's good to be here with you. Some of you I know, and I don't see for many years, and some of you are new to me. So good morning or good afternoon to you all. Yesterday, when I was revising this talk, I took a look at what Aaron and Camila spoke before me. And well, by now you are tired of knowing that on one hand, we have the observed data of galaxies. On the other hand, we will have model data of galaxies, a library of galaxy spectra, and then we will choose, you choose your favorite methodology of statistical inference. And the idea is that, okay, we get to conclusions like a galaxy X has a star formation like this and this, and a chemical enrichment history of et cetera, et cetera, et cetera. And what I want to do today is actually to bring attention to one ingredient, which is kind of hidden on the model data. Can you see my mouse when I move it, or?
Yeah. Yes, we can see it.
Okay.
Yes, we can see it.
Just thank you. And so here I want to go back and talk about a little bit of the stars which are hidden into the model galaxy's light. And my background is from stellar spectroscopy, so I end up going towards a little bit of a higher spectral resolution than what Aaron and Camila talked before me. So let's see what is a stellar population synthesis model. On its simplest description, I think we can say that is a library, a grid of templates, which we know very well how to parameterize in terms of ages, abundances, initial mass function, gas, dust, and etc. And why do we care to understand this ingredient, which kind of feels hidden into the whole process of studying galaxy light? And the way that I usually put it is that we know from the current paradigm that most of our universe is not visible light, is dark matter and dark energy. But even if it is so, what we observe is light, at least in 99% of the astronomy cases. So even if light is a minor component, we have to be very confident on how we understand it and how we interpret this light, because this is really what we have in our hands to study. And when we are talking about galaxy evolution, the light is coming mainly from stars, gas, and dust. So if we don't understand exactly the stars, gas, and dust, which are hidden in this galaxy, we cannot interpret actually the light of the galaxy. And this is where we come to stellar population models. Without them, we will not be able to understand the age distributions of stars in the galaxy, its star formation history, chemical enrichment or metallicity distribution function, stellar masses, ionizing population, dust content, initial mass function. So, and this is true for any system that we cannot resolve in individual stars, which basically is most of the universe, be it a galaxy or a stellar cluster. I was seeing in Camilla's talk that actually JWST is now looking into globular clusters in high redshift galaxies. So it still is systems that we cannot resolve into stars. So this means that we need to rely on the stellar population models. And this is mostly for the students, if there are any here, but I always like to remember where we came from. So I have 2 slides on the historical background of this field. And the first one to use these terms to distribute the stars in terms of populations was Walter Baade. And in the 40s, he observed the color magnitude diagrams in ME31, ME32, and NGC 205. And then he built this very interesting color magnitude diagram, and he concluded that the stars could be split between 2 populations. The shaded area are what he called the population 1, and this other hatched area is what he called population 2. And he made the comparisons. He says, look, this behaves like the stars in our neighborhood, what he called the typical HR diagram. And these ones are behaving like globular clusters that we observe in our own galaxy. So it was the first time that an astronomer was bringing together stellar evolution, galactic and extragalactic studies. And I find it quite interesting to look, for instance, the kind of color magnitude diagram that we are observing right now. So I'm just putting here a color magnitude diagram observed from Gaia, and actually from a couple of years ago. Now it's even more dense. And I find quite striking the evolution that we had in terms of observations. We started something like this, and now we are jumping into something like this in terms of resolved studies. I find this quite beautiful. Talking about stars, not the galaxies, but well, that's my background. And the second historical note that I want to make is about Beatrice Tinsley. She was the first one to develop stellar population models as we know them today. So this is an example from the late 60s on a library of SEDs of galaxies that she built. And she brought together, she brought into this recipe of mixing ingredients. She was talking about also about the chemical evolution and how this would impact the properties of the galaxies that we observe. So I think that I'm not wrong if I say that what we use today in terms of stellar population modeling are updates on these ideas that Tinsley developed. And we end up today with a huge variety of stellar population models. And this is something that we need to choose when we include into galaxy evolution studies when we want to do SED fitting. And there is a website organized by Jakob Walscher. I admit that I don't know if it's updated, but he was trying at least to keep a list of updated list of all the stellar population models that are available in literature. And at least it's a good starting point to have a sense of what is available. And what I see is that, well, it's not an easy choice. So among all these options, what is exactly that we do? How will we choose the best model for our science case? And this is not an easy question to answer. What I see in practice is that rather frequently, the models are used as black boxes, and this is not a good strategy. And I like to mention these 2 quotes. One of them is very famous in the statistical group, that all models are wrong, but some models are useful. And it's our job as scientists to understand which models are useful for our science case. And another quote that I like to remember, I watched Gustavo Brusual give a lecture on modeling as well. And then he said something which is very simple, but it's very important to remember that a model cannot be better than its ingredients. So when we choose a model of stellar population, it's a smart idea to have at least some sense of what are the ingredients which are inside these models. And this is what are the ingredients? This is the simplest possible case of explaining an ingredient of stellar population synthesis models. So we will have to choose an IMF. We will make a choice on the stellar evolution tracks or isochrones that we want to represent the evolution of these systems. We need to choose a library of stellar spectra, and this library of stellar spectra is the layer which makes the stellar evolution visible. Without this layer, we cannot really transform our ideas of galaxy evolution into something that we can combine with the observations. With these three very simple ingredients, we are able to produce simple stellar population models. This can be much more complicated, but I will stop here in this aspect because I want to bring attention to this specific ingredient, which is what I mostly work with. And here on the terms of the options that we have for grids of stellar spectra, there is also multitude. There are hundreds of options there. But without getting into too much into this path, we can broadly divide these grids into two kinds, an empirical or a theoretical library. And to give a lot of details on this, I will have to start a new talk, so I'll just ask you to believe in me. Let's say when this slide is trying to summarize what are the advantages and the disadvantages of using either an empirical library or a theoretical library. Of course, this is my personal take. We can comment this more if you want. But in terms of, let's say, an empirical library, well, the stars are real. So even if we don't make sense of them, even if they are weird or we don't understand them, they are real. So they are physically motivated because they really represent nature. Of course, when I say this, there are several observational issues there, and it's not exactly trivial to build a library because we will have to face problems with flux calibration, signal to noise. We have to choose a compromise between wavelength coverage and spectral resolution. It's very difficult to build a library where you have both a large wavelength coverage and high spectral resolution. We have to tag each one of these stars in terms of stellar parameters. And this is also a different discussion. But with some care, we can do this. We managed to do this. What is very difficult to do is actually to have a coverage of the parameter space that is not limited to our local volume. It's true that as the decades are passing, what I'm talking about local volume is growing. It's the example that I gave when I compared the SMD, the color magnitude diagram from BAD with what Gaia is getting now. So as the observations improve, we are able to resolve more stars, but it will always be limited. And this is an issue because the coverage of the parameter space is an imprint of the star formation history of the system. So if we want to observe galaxies which have histories which are very different from our local volume, we just don't get these stars around us. And this is where exactly the theoretical libraries will jump in, because we are able to cover this in as we want. So we have known atmospheric parameters because they are given as the input of the models. We don't have issues with the signal to noise. We can cover large wavelength windows with high resolution. So this is a given in the model. Of course, this may not be easy. It may be time consuming, especially depending on the physics that you are including in the atmosphere. It demands computing power, but it can be done. The problem is that well, they are still models. And as I said, I mean, a model cannot be better than its ingredients. And we are well aware that these models have inaccuracies because we don't know the opacities super well. What we know about the physics and the atmosphere of the stars is good, but it's not perfect. So we are again hiding ingredients there. So this is the kind of the main take that I can give in terms of the option that we have in stellar libraries. And just to explain how I call them, this is the way that me and my collaborators got used to call when we use a grid of stellar spectra, which is empirical, let's say millis, and we build SSPs with them, we end up with models, the stellar population models that we call semi-empirical. Semi because in the end, we are still using isochrones and or stellar evolution tracks. So we are still mixing theory and observations there. But the part of this observationality layer is coming from observation. So we'll call them semi-empirical models. Rather, if I'm using just theoretical models of atmospheres and stellar spectra, all the ingredients there are theoretical, and then I will call this model a fully theoretical model. There are other ways of combining these ingredients, but at least for the narrative of this talk, I'm focusing on just this dichotomy here, that either I use empirical grid of stellar spectra or a theoretical one. And we wanted to investigate this choice. What happens if we use empirical versus a theoretical grid, knowing its advantages and disadvantages? So most of the results that I will show here are published in this paper from 3 years ago, when it was Gustavo came here to visit me in Brazil, and then we investigated this question. So our idea was to answer 3 specific questions. We know of the limitations of theoretical libraries. How do these uncertainties in the atmospheres will affect our predictions in the stellar population models? So this was question 1. I will try to illustrate. I don't know how many of you are familiar at looking into the stellar spectra component, so I'll try to illustrate this, what I mean by this problem. And on the other hand, we know the empirical libraries, they have a coverage of the HR diagram, which is sparse. And so question 2 that we wanted to answer, how exactly these are going to affect the predictions of the models. And a third question that we wanted to address is, well, as I was saying, we have to tag each star with a temperature, gravity, and metallicity at least, or other chemical abundances. And these tagging have uncertainties. And so this tagging carries errors. And if we consider that there are random errors in this tagging, how this is going to affect us. So let me try to illustrate what is this question 1 that I want to answer. What I'm showing here is very heavy with information, so I'll try to make a sense of this for you. Here on the left side of the slide, what I'm showing is in black are models from a library that I published in 2014. And then in orange, I'm showing a bunch of stars. In this case, they are millis, overplotted to the models for a given bin in a parameter space. So the bins are indicated. The bins are indicated here in each panel, and then we can see that overall, we can say that the models reproduce well the loci of the observed stars. But this is on the overall. If we increase the resolution, the spectral resolution, and we try to look into details, this is what I tried to summarize here on the right side of this slide. And what I'm showing here in black is the mean residual between the model, is the residual between the model and the mean of the observations. And then in orange here, what I'm showing is the root mean square that is given me by the observations inside each of these bins in temperature and gravity. And what we can see here, if we go towards warmer stars, I was not able to do this for hotter stars because, at least in millis, there are so few of them that I cannot really build bins of stellar parameters. But here in the case of the warm stars, we can see that the models, they fall easily inside the variation that we see in the observations. So we are safe there. As we go towards cooler stars, the picture starts getting more complicated. And there are regions, let me point here to the one around 4,000 Kelvin. And the picture here is that actually there are specific regions of the spectral coverage where the models are systematically off compared to the observations. The reasons for these offsets are most likely opacities, problems with the opacities, which are by itself a very difficult ingredient to model. So we know about these problems. So if we know there are systematic problems here, what happens when we use this in stellar populations? Because we are carrying this into the modeling. On the other hand, we know that the main disadvantage of the empirical libraries is that they have a sparse coverage of the HR. And here I am illustrating this in the right panel. I'm showing in black the stars from millis. We can do better now. So for instance, with Extruder library, we can cover this area here that millis is not reaching, but at least for this exercise that we did, we were still using millis. So in black, we have the coverage of millis, and then the shaded gray area is what the models are covering. And the coverage of the models, they are specifically chosen to cover a wide range of stellar evolution tracks. And this panel here, we are talking about the solar metallicity, and we can see that there are, as I was mentioning, spaces where we cannot really cover the stellar evolution tracks, but it's a good coverage anyway, because where the stars are is actually where we most need them. So this is okay. So it is a good coverage. Where we don't have stars, they are more rare. This corner here is a bit more complicated because this will impact very much the infrared, but let's say that the coverage is good for solar metallicities. As we go towards low metallicities, well, the comparison gets very scary. And this is very important in the current times when we are looking at high redshift galaxies. We are not anymore talking about this regime. We are talking about this regime where we have very few empirical stars to cover everything that is needed. So this is the limitation of the empirical libraries that we have to have in mind, especially if we are talking about high redshift galaxies or even nearby galaxies, but we are talking about star forming systems or even old systems which have chemical enrichment, which is very different from our local volume. And then the third question, which refers to the uncertainties that we have in the stellar atmospheric parameters. Here I am showing the error in stellar parameters as a function of temperature. And at the time I split between precision and accuracy, but without entering into too much detail, we can see that in the best case, we will get 100 Kelvin of error in the cool stars, and then we reach towards 1,000 Kelvin of uncertainties in the hot stars. And this is what we wanted to see how it's going to affect the models. So, okay, how are we going to address these questions. We go back to our ingredients here, how to build a stellar population model. We are fixing the IMF, which we chose to be Chabrier. We are fixing the stellar tracks, which we chose to be the parsec tracks. We are fixing the code, which is the same as BCO3, Galaxev. But we are changing here the grid of stellar spectra. We are using 3 different grids, the empirical millis, a fully synthetic one with a good coverage of the HR, which is the one that I published in 2014, and another theoretical one, which has the same ingredients as these, so the same problems with the opacities, but it has the HR coverage of millis. So in this way, we actually hope to split the problem and make a controlled experiment. So we are calling the synthetic effect the problems that we create in the stellar modeling when we compare millis with its synthetic counterpart. So the HR coverage is the same, but we are carrying the problems with the opacities. We will call the coverage effect what happens with the models when we compare the synthetic library, but computed with the HR coverage of millis, which is sparse, against a library with a full coverage of the HR diagrams. This is what we call the coverage effect. And in the case of the question number 3, we will say randomize the parameters. What happens when we build models based on millis, but we apply variations in the temperature and gravity according to what we know of these uncertainties to be. So I want to show you now the results that we got, first in terms of model-model comparisons. First, we wanted to look into the colors. So we computed all these variations of models for a range of ages and metallicities. We computed colors. In this case, they are Sloan colors. And then we made the differences. So we are showing here the distribution of delta color when I'm studying the synthetic effect that I explained before, the coverage effect, and randomizing the parameters. And what we see here is that the coverage effect is the one which will impact most the colors. The different colors here, I'm talking about colors and colors, sorry, astronomical colors here, the Sloan, and then the static colors here are showing the different colors here are showing the different metallicities. But what we can see through these comparisons is that the coverage effect will have a larger impact on the prediction of our colors. The synthetic effect will also impact, but it is smaller than the problem that we are if we have just a sparse coverage of the HR. And randomizing the errors and the parameters has the smallest effect of them all here. There is a different way of showing this just as a box plot, but just to show that the coverage effect will always have a larger systematic effect and a larger random effect. So this is the kind of problem that we expect to see if we are using just millis or other empirical libraries. So the message to take home here, at least as we see it, if your science case is largely based on photometric data, we think that it's actually safer if you use SSP models which are based on synthetic libraries, because you are, at least the errors that you are introducing there are smaller. And then I want to show also the effect on spectral indices. I'm not even sure if I have to explain what spectral indices here are, but at least again, if there is students around, and indices is a rather old way of studying stellar populations, but they are, in a way, they are very convenient because they are a way of synthesizing information in the spectra into just numbers. So I just got some pictures from literature, and then basically the spectral index and most of its use, it's a way of measuring the equivalent width of a strong absorption line. So especially in the medium to low resolution that we see in the case of galaxies. And we can define several indices, picking up different features, different strong features in the spectrum. And they will be sensitive to different chemical elements. And as I mentioned here in this analysis, we decided to use indices because they condense information, spectral information, in a very neat way. Rather than looking all the time at the spectrum, pixel by pixel, we can look into indices. And then we made the same comparisons as before to study the coverage effect and the synthetic effect for a variety of indices which can be measured in the Miller's wavelength range. And here I'm showing the variation, again, the distribution of the delta index that we are measuring with this model-to-model comparisons. And the red distribution here is indicating the synthetic effect, the green is showing the coverage effect, and then the blue, the distribution from randomizing the parameters. And what we see here, I'm not even showing all the indices, but what we see here is that the picture is much more complicated. If we look, for instance, at the 4000 break, this is an index which measures the 4000 break. The biggest error is coming from the coverage effect. But if we look rather to the iron 5270, which is a widely used region in the spectrum to measure metallicity in galaxies, the biggest error is coming from the synthetic effect. And both indices are widely used in galaxy studies. So we end up with a complicated pattern because what is best will depend on the index that you are in the wavelength range that you are looking at. And here I would like to show, just to show what happens with age. This is a different representation, and I'm showing just index here versus index here, where here I have in the y-axis, I'm showing the effect of varying the parameters. And what I want to illustrate here is that even though here I am like collapsing all the information of all the metallicities and all the ages and trying to have a sense of the broad behavior, but actually we know that these answers will vary with the parameters. So I'm showing here the colors are indicating different ages. And I call attention here for the TIO, where when I'm talking about the young ages, and TIO have been used to study IMF, for instance, but you can see that randomizing the parameters, even though for old ages it doesn't matter that much, it will matter a lot for indices, for some of the indices like the TIO. So all this that I'm trying to tell you is that it will vary with the wavelength range, with the age range, and with the metallicity range that we are studying. So I would say that the message to take home here is, if your study is based on spectra, the choice needs to be made on a careful way, because the optimal model will vary with small spectral windows. So there is no easy answer here. And then you can tell me, okay, so far so good. I'm showing model-model comparisons. But what really happens if we use all these models and the effects, the coverage effect, the synthetic effect, to study observations? Because in the end, we want to understand what happens when we study galaxies. And of course, this will depend a lot on how you are studying your observations. At least for the perspective of this paper, we made a choice of studying what was happening with the spectral fitting. We used the starlight in our test, but I believe that this is applicable to any other spectral fitting code, the PXF, Firefly. This is an illustration of what the spectral fitting is. It's not from my papers, just from literature, where we will try to reproduce the observation pixel by pixel, exactly as we do in the SED fitting. We can either be fitting points of photometric data or points of spectral data. And what we have done, we gathered a collection of 100 nearby galaxies in SDSS, and we fitted them with all these models that we built of this our controlled experiment. And then we compared the mean ages and metallicities and reddening that we were obtaining for these galaxies. And this is illustrating what the synthetic effect is causing to our interpretation of galaxies. These are, in most cases, old galaxies, because being SDSS, we are looking at the bulge. So even if the galaxy as a whole was relatively young, at least we are looking into the bulge of these galaxies. But you can see, so we have most of them are old, but you can see here a tail of younger systems. And what we see is that the synthetic effect will not affect the measured ages, but it will affect the measured metallicities in a way that is not systematic. Towards solar metallicity, there are almost no difference, but as we go towards lower metallicities, we see here a difference between the models based on empirical libraries or synthetic libraries. On the other hand, when we look into the coverage effect, the problem is reversed, actually. We will not have a strong effect on the metallicities other than actually increasing the spread of the measurements, but we have an impact on the ages, specifically in the intermediate ages. And here we are talking just about visible, and we are already seeing an effect here on the inferred ages. And what do we do with this? Actually, I am not sure, because if you need both the best age and the best metallicity, then there is no easy way to choose what is the optimal model for you. I hope I'm not discouraging too much the young astronomers. So I'll jump to my conclusions. And in Camila's talk, she was pleading, please don't use SED fitting tools blindly. So I will add my own comment, please don't use the stellar population models blindly. It is important to have at least some sense of the ingredients that are hidden there in the models, because these will affect your results. And therefore, it might affect the conclusions that you are drawing on your galaxies. This is, I would say, the takeaway message, that there are no way around these problems. These problems are there. And we as scientists, we have to choose which of these problems we feel more confident to live with, and measure our conclusions in the light of these uncertainties that currently we are unable to get rid of. And in more specific cases, conclusions from this work is that the coverage effect or the coverage of the HR diagram will affect the predicted colors more than the other uncertainties that we were talking about. In the case of spectral indices, and then this means that how we can understand the spectra of galaxies in general, the picture is more complicated. The synthetic effect affects more regions, but it's still comparable. I think it's about, of the indices that we studied, 18 were mostly affected by the synthetic effect, and 12 were largely affected by the coverage effect. So, and then in the end, we end up with this hybrid situation where some indices are more sensitive to one or the other. And then it's difficult for me to say what is best to do in that case. We tested that the random errors in the atmospheric parameters are minor. So we got confident that at least this is something that will not affect much the stellar population modeling. There is a work by Mauricio Salaris from several years ago that actually showed that the systematic errors will matter, but at least we are confident now that the random errors in the parameters is not a problem, at least in the light of all the other problems that we are facing. And the synthetic effect, when we apply all this to galaxies and to the rival stellar population parameters of the galaxies, the synthetic effect will not affect the mean age, but it will have an effect on the metallicity, and the coverage effect is the inverse. It will affect ages, specifically the intermediate ages, but it will not impact in an important manner the metallicities. And gladly, at least the reddening is virtually unaffected, so at least we can trust that. So thank you very much. I hope I didn't lose you over all these super detailed technical explanations of the ingredients, and I am open for questions.
Thank you very much, Paula. That was a really nice reality check of people using basically any model of stellar population. So that's very good. Okay, so now we open the floor for questions. So I think I have Scott. Scott, if you want to unmute and.
No, I was just clapping. It's a very good topic.
Oh, sorry, I didn't. So I have, well, Laerte.
Hi, Ignatius. Thank you for organizing this series of seminars. And Paula, very pedagogical talk yours. I have a question regarding the issue of the chemical patterns, because probably most of the models we use follow the chemical pattern of our galaxy, and probably this is very different from what we see in other places. And I'd like your feedback about how you see this problem, and from the theoretical point of view, how do you plan or not to address this sort of thing?
Yes, we have addressed this from a fully theoretical point of view. This is how my collaboration with Gustavo started. So we have models which are fully theoretical, and then provided at least the alpha enhancement for old systems. The thing is, most people, and I totally understand, they don't like to use the fully theoretical models because of the problems that I showed here. So I didn't really want to get into too much of detail, but I was saying that there are ways to combine both the empirical and theoretical models. I mentioned very briefly, that was in the very beginning. Yeah, so I think that currently, the best strategy that we have so far is what is called the differential predictions. And this has been proposed originally by, as far as I know, by Felipe Progniel in 2007, and then Jakob Walscher and I. We explained this in a more systematic way in 2009. And this is the strategy which has been adopted mostly by Vazdeckis, by Conroy. There are problems there as well. So it's not if you use, because here what you are doing basically is using the differential predictions from fully theoretical models to correct empirical models. If you use different sets of models, you may end up with different corrections. So in the end, you just translate the choice that you have to make one step behind. But at least this is the best thing that we can do. So if we want to address, let's say, measure alpha enhancement in elliptical galaxies, I think that the best we can do now is, for instance, use Vazdeckis 2015, or there is the semi-empirical, there is one more recent model for the same group computed by Adam Knowles. So this is the kind of models that you are looking at. So what I call, or at least my collaborators call, differential models.
So you don't have, say, a single library able to address all types of galaxies right now?
No.
Mm-hmm.
No.
Okay.
That is, that goes back to what Camila was explaining, that in the end, you have to be aware of your priors. And this is the inconvenient truth. It's very difficult. No model is good for all cases.
Mhm. Perfect. Thank you.
Any other questions? That I'm going to jump in with mine. I have, regarding the coverage aspect that you mentioned, there's also another layer on top of that, which is normally in the population synthesis models, the sampling of the age, let's say age axis, the age parameter, is much finer than metallicity because of the typical, basically you can constrain better in a way if you want in different units. So did you explore this issue that, for instance, in terms of metallicity, you usually have 5-6 entries, whereas for age you have of order 100 or so?
That is a good question. I did not explore that directly. And I think depending on how the methodology that you're using to compare the models with the observations, you might get different results. My gut feeling is that if we are talking about spectral fitting, such as the ones being with starlight, I have the feeling that it will not affect that much, because in the end, the codes will be able to interpolate between the models. So effectively, what the code will see is a better coverage, or at least a finer coverage in metallicity. It's true that the interpolations carry its own problems, but at least I have, my feeling is that it will not affect that much, but I may be wrong, so I did not test.
Okay, thank you. Scott, now it's a question.
Now it's a question. Well, it's sort of a reaction to this question that you just asked, Ignacio, which is that I understand, I have to say I've sort of stepped out of this field because my last PhD student working on this graduated a while ago and has gone off to bigger and better things, climate science, it turns out. But I was talking to the SAMI collaboration folks, and it turns out that their analysis of the SAMI data seems to indicate that actually the metallicity steps that are available in the current generation models are actually too large, and they're actually seeing interpolation effects when comparing to the SAMI data. And so they've actually gone back and started making new isochrones with their collaborators to actually put in much finer metallicity steps into the isochrones, and are then going to be making new models based on those finer metallicity steps. And their first attempts at doing this, actually, it turns out they're also doing this with alpha to iron in a broad sense. And their first steps in doing this have actually shown that they're getting better comparison to the SAMI data that they have than the previous generation models. That being said, I don't know who actually, I mean, I got all this from Jesse van de Sande, who was visiting Groningen a few months ago, but I do not know any details of it other than to say that this is something I actually have been looking for some years. I'm glad somebody's doing it, but I don't know much more about it. Maybe Paula knows more about it than I do. I don't know if you're connected with the SAMI folks. Anyway, but I think there's going to be another generation of models coming in the next year or so, which might actually answer Ignacio's question directly. So.
Cool, thanks. I'll keep an eye open. I didn't know.
I mean, it's a very interesting point because somehow it also connects back with what you were saying, that you compare a full spectral fitting, line strengths. It just depends so much on how variations on the parameter changes this. So normally you expect that on the shape of the spectrum, age is going to have a dominant effect, so to speak, whereas metallicity will introduce variations. But then if you go to a line strength, perhaps metallicity is more important. So I guess it all depends on what you're doing with the...
Yep.
So, Ralph?
You hear me now?
Yep.
Yes.
Okay. I have a question to the, first of all, thanks for the talk, of course. So my question is on the stellar libraries. So 80% of the massive and most luminous stars are binaries. And is that in these libraries considered, or are that all single stars and you have one G and so on?
That's a good question. Here in these specific results that I'm showing, I'm considering only single stars. But Gustavo has some work dedicated to the effect of binaries. I hope I'm not misquoting his results, but from what I remember, this will affect rather significantly the young systems, but not the old systems. So in that case, we go back to what Laertes was commenting. You end up not having a good answer, a good solution for all the systems. But in the young systems, apparently the binaries cannot be ignored.
Mm-hmm. Could I continue with another question? So besides the binarity, these massive stars have also winds, and that contributes, or maybe even some dust emission nearby, which contributes to the near-infrared or even longer wavelengths. I guess this is also not covered in these stellar libraries, or is it?
Yeah, it depends on the library. In this aspect specifically, the library that maybe I am not updated, so take this with a little bit of salt, but at least in my contacts, the library which cover these effects, at least for the visible and the UV, are the libraries by the group of Klaus Leiterer. They do a very interesting job into taking into account these effects. So they treat the massive stars very carefully. Mm-hmm. So it's not by coincidence that for the star-forming galaxies, usually it's better to go with the models by starburst 99 and descendants, let's say, exactly because of what you are pointing out. They do a very good job at those stars.
Okay, thanks a lot.
You're welcome.
So Paula, one thing that in your analysis of the models versus the observations, so in principle, the observations are the way they are. You cannot have so many stars because you have a finite amount of telescope time and resources. So Miles has 1,000 stars. So have you considered how many stars would be the optimal for especially I could imagine in the fast changing phases. So would we be happier having 3,000, 4,000, 10,000 stars?
I think my feeling is that it doesn't matter so much how many stars, but actually more if we manage to pick the regions which are not well covered. Let me go back to the AGR. Yeah. So I think that if we get an order of magnitude more stars, we will end up having most of them here in the where the stars already are. And one strategy is actually to try to target the rare stars. And XShooter did this, at least Scott, correct me if I'm wrong. They managed to cover the tip of the red giant branch really by picking up the rare stars, and they were hunting them, and also the low mass stars. So I think we will have to do something on those lines. So Scott, yeah.
So yeah,
we have to hunt them.
That is what we did. We took catalogs of known AGB stars, mirror variables, whatever was up in that part of the, in part of the diagram, as well as M dwarfs, and added them. In fact, that's the first thing we did in the XSL survey was try and go after those stars. I would say that the next generation of wide field surveys like Foremost and Weave and things like that will actually produce millions of stellar spectra. The question is whether or not they cover enough of the HR diagram, as Paula is saying. And my feeling is probably not, unless we're very careful about doing it as a specific project in Foremost or Weave or whatever those next generation of surveys are going to be. And I can tell you that those surveys are already well defined, and they don't, at least the Weave survey, which I am intimately familiar with, does not include those kinds of stars as a part of the survey. However, thankfully for both projects, there is open time available. And I've been talking to people about actually using some of that open time. Although as project scientist for Weave, I feel always guilty about, asking for time on the instrument when I've already done so much work on it. But asking for time to actually go after those sorts of stars with the next generation of surveys, because the data will be better than what we could do previously. That being said, XShooter is still the best instrument to do this with if you want to go beyond the optical in either direction. Maybe there's going to be another generation of XSL type surveys in the future, which would be great. But it's hard to get, as you say, Ignacio, it's hard to get enough telescope time to do it well. Even with XShooter, even with the XSL survey, we just didn't get enough stars, in my view. So we got a lot, we just didn't get enough. So
Thank you. It's actually a rare pleasure to have both of you having a theorist and an observer on side by side. It's actually fantastic because it goes back to the idea, for instance, one of the strongest part of the analysis of stellar populations was massive galaxies, this business of high metallicity, the IMF and all those things. And when you realize that basically the models have so few stars and the full analysis depends just on a handful of them. So what is the best way to go? So I mean, maybe this is a question for you both. Is it the observational or the theoretical aspect that will allow us to properly sample the high metallicity and high, basically giant versus main sequence star regime to explore all these problems?
Honestly, as an observer, I'd say I have to hand it over to Paula because, in fact, when I asked this question, I said, Paula, come and help us, right? Because in the end, we don't have stars like that around us. I mean, that's what Laerte was pointing out earlier, is that I would love us to have all the stars and all the galaxies nearby enough that we could go and observe them. But either we have to wait until the ELT generation of telescopes and push into the right wavelength range so we can actually get, diffraction limited spectra of giants, even let alone main sequence stars in other galaxies that are more like the stars that we see across the universe. But I don't think that's going to happen. We really need Paula and her collaborators to do the job for us and to really, what has been great, I mean, I have to say this because I've been working with Paula for a long time and I really do appreciate the work that she's done, is that they have thought so hard about all of the problems on their side. We haven't thought actually quite as hard as they have about the problems on our side. And it's great because Paula and her collaborators keep us in line because they say that we can do this with theory, but you have to understand where the theory stops. And I think it's been really good to have that back and forth with the groups, because without it, we I do think that I'm glad to see some young people on this call, a few, because I think there's a younger generation of people who do use, as Paula was saying, who use stellar population modeling as black boxes. And those of us who are old and gray at this point, we realize that that's not a good thing to do, but teaching our students is the most important thing there. That's what we try and do, right? But anyway, I think that, Paula has made a heroic effort over the last 2 decades to make sure that we're honest about this, and also providing us with enough information that we can say, yes, that's where we're missing and that's where we need to do more work from the observational side. At the same time, we go back to her and say, your models don't do this. And she says, oh, okay, let me go fix that, right? She can't always, but we get closer every time. So I think it's been a great back and forth, and it's really great to see all of this now, because this is what I wanted a decade ago, and it's nice to see it's all happening again. So great. Excellent.
Thanks so much.
Thank you.
So that was fantastic, actually. So, Paula, closing remark then on this. What's your
closing remark? Yeah, I think that both observations and models, they go hand in hand. I totally agree with Scott. I think no matter how much the observations improve, there will always be a local volume that we can resolve stars. And beyond this local volume, we only have models. But if we don't double check the models incessantly with the observations, at some point the models will not be useful, right? So I think that both things will go. I don't think we can cover with observations all the coverage that we need in all aspects. I really don't think so. But we do need this double checking and sanity checking with observations constantly. Otherwise, the models will be more trouble than solution.
Okay, well, that was great. I mean, I really enjoyed so much the discussion. The talk was fantastic. So thanks so much, Paula, for your contribution. And everybody, hope to see you and many more next time in 2 months' time. We will have actually, Scott, somebody from your institute, from Captain, Wang Yang, will be giving us a talk on November 13th. So thanks so much. This will be posted in YouTube. And yeah, thanks so much, Paula. That was really great. Thank you. Take care.
Bye.
Bye-bye.
Wow.